Welcome to 20th lecture for the NPTEL course on computer system optimization for machine learning. Today again we will give you a brief recap whatever we discussed in the last lecture, and then we will continue on parallelism in DNN training. Right. So, in the last lecture we discussed data parallel training, where we replicate the model across all the GPUs and then we shared the inputs among the GPUs, so that each GPU can train on the model on different data parallelly, right. Of course, here the issue was the communication, like we cannot say that we will synchronize all the GPU or synchronize all the training happening on the GPU at the end of the training at each GPU, but we need to synchronize in between. So, we saw that for communication we can employ all to all communication, but which has higher overhead. We can employ ring all reduced communication, which has low overhead, but then at the end of the day the amount of communication is bottlenecked by the number of training data. So, that is why we can say that if we want to keep scaling synchronous SGD, we have to keep increasing the batch size. Whenever we say batch size, that means after those particular images we will perform the communication. So, if we increase the batch size, if we say that we will perform the communication or we will perform the synchronization after more number of images, then yes, we can reduce the communication, because then the number of times we need to communicate or we need to perform the communication for the entire training is less. But the problem is, we cannot increase the batch size as much as we want. So, this particular figure is showing the ImageNet top 1 validation error with respect to different mini batch size. So, as you can see that the validation error does not change much till the point when the mini batch size is 4000, but then when the batch size is more than 4000, then the validation error increases a lot. So, that means the larger batch sizes actually harm the generalization performance, right. So, this particular figure is actually saying that there is no free lunch. You can increase the batch size, but then the validation error will be reduced. If you can decrease the batch size, then the communication overhead will be reduced, right. So, that nothing is coming for free when it comes to systems. Okay. So, this particular figure is showing epochs per second, which is you can think as like throughput versus accuracy per epoch, right. The naive, not naive, the most synchronous stochastic gradient descent, where we maybe we communicate after each batch or after each mini batch, of course that will have higher accuracy per epoch, but then the throughput will be less, because the throughput will be bottlenecked by the communication. Now, on the other hand, we can have like naive asynchronous SGD, where we do the synchronization after each GPU finishes its execution for the entire data set assigned to it. We can do that, that is the naive asynchronous SGD. There maybe our epochs per second will be very high, the throughput will be very high, but the quality of training, the accuracy per epoch will be low. So, the common problem is, in synchronous case the communication overhead is problem. In asynchronous case the stall gradients are the problem, because in asynchronous case we are not changing we are not taking account of the other data set which is being trained on the other GPU, right. So, perfect linear scaling between performance with the workers is almost impossible. So, that is why there exists some technique which perform this asynchronous stochastic gradient descent with stale gradient handling. Okay. Now, to summarize the data parallelism in DNN training, we saw or we discussed that it is an efficient training method where the communication time is independent of GPU workers with ring all reduce. It is super easy to implement. You can just have this all reduce before parameter update, right. That is how this data parallelism can be implemented, but it is challenging to scale. Like, we need to balance the statistical and hardware efficiency. Whenever we talk about statistical efficiency, that means we are talking about the quality of the training, like how the model is converging, what is the accuracy per epoch. So, it is very difficult to balance the statistical and hardware efficiency in the case of data parallelism during DNN training, and frankly speaking data parallelism does not work for large model. So, for the large model the communication overhead becomes very prominent. and that is why this model parallelism came into the picture. Now, the main reason the data parallelism does not work for large model, because many a time it can happen that the large model may not be fitting onto one GPU, right. So, that is why this model parallelism is absolutely necessary when the model cannot be hosted in the memory of a single GPU. So, remember the GPU memory is less, like 80 GB probably is the best memory in the state of the art GPU, maybe 120 GB, but again if the GPU memory is 80 GB, we cannot say that we can fit a whole 80 GB memory or whole DNN with 80 GB of weights, right, because again each and every cell or each and every bytes of the GPU cannot be used by the model weights. There are other things also, right, activations and all the other things. So, that is why this model parallelism strategy can be incorporated, where we divide the model across the machines and replicate the data. So, in this particular case you can see that our model has maybe 5 layers, the first layer go to machine 1, the second layer go to machine 2, and so on and so forth, and then while training we need to feed the same data to all the machines. Okay, we cannot say that we will feed different data to all the machines, we need to feed the same data to all the machines, because actually we do not need to feed the same data, but I mean the effect of same data should be going to all the machines. Now, the advantage of the model parallelism is we now have increased total memory capacity, which can hold a bigger model. The communication is now point to point. So, as you can see, the communication will be now only from machine 1 to machine 2, machine 2 to machine 3, machine 3 to machine 4, just to communicate the activations from the previous layer to the next layer, right. During back propagation, the communication will be from machine 4 to machine 3 and so on and so forth. So, there is no like all to all, there is no requirement of all to all communication for model parallelism. The communication is point to point, so it is less expensive, and we can employ small mini batch. So, it will have better statistical efficiency. So, just to give you an example, let us say we have 4 machines. So, we can break the DNN model into 4 parts, and this is how the model parallelism work. Like we compute the forward pass, the blue denotes the forward pass, the green denotes the backward pass. So, we compute the forward pass on the first machine, and then it sends the data to the second machine, and then third machine, and so on and so forth. When the forward pass is computed in the fourth machine, then it also computes the error. Now, depending on the error, the backward pass happens in the fourth machine, then it will go to the third machine and second machine, and so on and so forth, right. Now, when the backward pass reaches the first machine, that means all the weights, all the delta W's or all the changes in the weights have been computed for the entire DNN. That also means that we can update the weights. After that, the next forward pass starts, right. That is the model parallelism. Now, that means we can parallelly execute the model, or we can break the model into different parts, and those different parts can be executed onto different GPUs, right. That is the model parallelism, but the disadvantage is the underutilization. So, you can see that whenever machine 1 is doing something, then machine 2, machine 3, machine 4 is not utilized, right. Similarly, when machine 3 is doing something, then machine 1, machine 2 and machine 4 is not doing anything. So, that is the underutilization. I mean, we are not utilizing the GPUs effectively or properly. Also, you cannot mask the communication. Although this communication is point to point, we cannot hide one computation behind the communication. In data parallelism case, we could hide some computation behind the communication, so that the communication latency is masked, right. And another biggest question is how to partition the model over the worker. I mean, of course, whenever we talked about DNN, we saw that the layers are not homogeneous, right. Layers are not of equal sizes. So, we have to carefully partition the layers, or we have to carefully partition the DNN across different GPU devices, right. So, due to these disadvantages of model parallelism, there exists something called pipeline parallelism. So, before pipeline parallelism, or before discussing about pipeline parallelism, let us see the disadvantages, or let us quickly recap the disadvantages of data parallelism. So, data parallelism, as we already discussed, the communication overhead is very high. So, in this particular graph, they are showing the communication overhead of different number of GPUs for different models. So, as you can see, when the number of GPU is high like 32 and the model size is also high like VG16 has like more than 1 billion parameters, I think, right. The model size is very high, correct. So, if the number of GPU is high and the model size is also high, then the communication overhead is almost like more than 90% or maybe 95 or 99%, like more than 99% is of the total execution time is just spent on communication. And in this case, in this particular example, 8 V100 GPUs with NVLink was used and then NCCL library was used. So, that is the disadvantage of data parallelism. Means in data parallelism the communication overhead is extremely high. In model parallelism, we already discussed that the resource utilization is very poor, that is why the throughput is very low. I mean, throughput is low means we cannot execute any other model or any other data set whenever one particular data point is getting trained or whenever the model is getting trained with one particular data point. And that is why this pipeline parallelism came into the picture. This is similar to model parallelism, but use multiple batches in pipeline fashion. So, let us say we have 4 batches, in this case 0, 1, 2, 3, these are the 4 batches. Whenever you see yellow, that is the forward pass, blue means backward pass, and I think this is orange or maybe light pink, it is baby pink means wait update. Okay. So, in this particular case we are performing this the entire training onto 4 batches, and we can do this training, we can do this forward pass as well as the backward pass in pipelined fashion. Okay. So, as you can see, like whenever the forward pass of 0 is happening in GPU 1, then the forward pass of this first batch is happening in GPU 0 and so on and so forth. So, after all the forward pass is over, then the backward pass starts. So, whenever the backward pass is over, then the wait update for all the layers are happening. So, that is how this pipeline parallelism work, right. So, it is similar to model parallelism, but it is using multiple batches in a pipeline fashion, right. Now, there are different variants of pipeline parallelism. The one which we just discussed was published in NeurIPS 2019 and the paper name is GPipe. Again, you can go ahead and read the paper to know more detail. So, in this particular work, there are micro batches which help reduces the bubble. So, these unutilized GPU cycles are called bubbles, which this particular pipeline parallelism reduces the bubble compared to model parallelism, but still it exists, right, it is not minimized. So, and one another important aspect of this GPipe is there is no staleness. This is close to batch SGD, batch stochastic gradient descent or batch training, right. We are performing forward pass, then backward pass and then wait update. So, that is there is no staleness, correct. Now, instead we can perform inter-batch pipeline parallelism, which was published in SOSP 2019 and the paper name is PipeDream. You can see that pipeline bubbles are minimized, right. There is almost no pipeline bubble, very few pipeline bubble, but then some staleness is introduced, right. We will see how the staleness is introduced. So, overall there are challenges with pipeline parallelism. So, first is work partitioning. We need to minimize the load imbalance between the partition layers at each worker. So, we cannot say that one particular worker has like 80% of the model, then the execution time of that particular partition will be too high and then we cannot do this pipeline parallelism, right. And then another challenge, another implication of this work partitioning is to minimize communication across workers. If one particular partition has most of the parameters or most of the computation, then it will have like more communication between the next partition, right. Then the major challenge is scheduling the forward or backward pass. Should we schedule an in-flight backward pass or should we schedule a new forward pass? So, that is another challenge with pipeline parallelism. Of course, staleness and convergence is another challenge in pipeline parallelism. So, let us compare this GPipe and PipeDream. So GPipe was the case where there was like simple like batch stochastic gradient process, all the 4 forward pass is happening, then 4 backward pass, and then weight update is happening. But in PipeDream they have introduced like automated technique which takes per layer latency in picture, and then they have this profiler plus optimizer. Now with all these things the authors use like dynamic programming to find the partition that minimizes the overall training time. So it's an optimization problem. So you know all the parameters of the DNN, you can profile the latency, the execution time of all the layers of the DNN, and then we can employ the dynamic programming to find the best partition which minimize the overall training time. So that's happens in the PipeDream. But GPipe is manual. I mean, you do the per layer profile and then identify the right layer partitioning. So it's a probably design space exploration search in GPipe, right? Now that's the work partitioning. In terms of scheduling, again GPipe is simpler. So in GPipe, first forward pass of all the micro batches are performed, which is followed by the backward pass for all the micro batches. So these are the forward pass of all the micro batches, and these are the backward pass of the all the micro batches. So that's a simple scheduling in GPipe. But then in PipeDream, one simple static 1F 1B partition is incorporated, right. So there are alternate forward and backward pass. So you can see that 3 3 4 4, so there is alternate forward and backward pass for all the GPU. So this is forward pass, backward pass, then this is forward pass, backward pass, and so on and so forth, right. So there is no like batch of forward pass and then batch of backward pass in PipeDream. Of course, here by doing that the pipeline is full, there is almost no bubble, and then this schedule are computed statically. So we don't need to dynamically schedule this forward and backward pass. So if we have like static schedule, that means it's just the schedule can be written in lookup table. We can read the lookup table and implement it in the runtime. So it's a cheap process, right. Now in terms of convergence, GPipe is unaffected. So we can think that the convergence of GPipe or the training in GPipe is similar to the data parallelism, with a batch size of B, where B is nothing but the micro batch size multiplied by the workers. So the convergence in GPipe is similar to data parallelism. We can think that I mean in the data parallelism we talked about the batches, right. Here we can think that batch is nothing but the micro batches, which is micro batch size is nothing but the 4. I mean in the previous case we had the micro batch size as 4, right, multiplied by the number of workers. So that's the batch size. So in the GPipe the convergence is unaffected, but in PipeDream the forward and backward pass for one mini batch are performed with different weight versions. So for an example, if you see, this is the forward pass of 5th mini batch and this is the backward pass of 5th mini batch, but between that the weights have been changed, correct, which is not intended. The backward pass of the 5th mini batch should be performed with whatever weights or activations which was performed with which was done with the forward pass of the 5th mini batch. Now due to that the model convergence is hindered. So one solution is we can perform weight stashing. That means we can keep multiple copies of the weights until and unless that particular mini batch is done. Means we can say that this we will keep a separate copy of the weight for this 5th mini batch until and unless the backward pass of the 5th mini batch is done. We can do that, but then again it will take more memory, right. So these are the disadvantage of PipeDream. Of course PipeDream allows to reduce the pipeline bubble, which allows to improve the GPU efficiency, but at the same time the model convergence is hindered, right. Now in general, of course there are many fancy techniques, which some of them which we will discuss in the later lecture, or maybe some of them we will discuss in this lecture also. There are many fancy technique which is very good in pen and paper to perform or to introduce the parallelism. But the general advice is the training method that adversely affect generalization are not adopted unless there is let us say some 10x speed improvement, right. I mean all those things like the PipeDream which we talked at the end, this is kind of against the generalization, like it adversely affect the generalization. So, these kind of technique are often not adopted unless there is a like 10 times speed improvement. I mean what actually happens, like there are so many parts moving, like there are so many parameters, there are so many things, so many activations that are moving which can go wrong in training large models. And that is why most often practitioners stay away from asynchronous methods unless that is absolutely necessary. So, for an example, I mean we will see training large models probably sometime later, I mean training very large recommender system which can have like trillions of parameters. Now, if we have those many parameters, I mean it can happen that I mean we can devise a very fancy parallelism technique, but then so many parts are moving, if we cannot synchronize properly, then the training convergence will like be harmed like drastically. Now, with that let us discuss the last parallelism in distributed training, which is tensor parallelism. So far we have seen data parallelism, model parallelism and pipeline parallelism. Tensor parallelism is again simpler. I mean in model parallelism and pipeline parallelism we have splitted the layers across the workers. If we have n layers, then we have probably assigned some of the layers to some of the GPUs, right. But then it might be the case the layer itself does not fit, a layer itself is so large that a GPU cannot handle it. It may happen, we will see whenever we discussed about large language model, we will see that it may be the case, right. And that is when this tensor parallelism comes into the picture. So, in tensor parallelism we split a tensor. Whenever we say tensor, that means we can see that we have a 4-dimensional filter, that is a tensor, that is a 4D tensor. We can split a tensor into n chunks along a specific dimension, and each device only holds 1 over n of the whole tensor while not affecting the correctness of the computation graph. Of course, I mean that we cannot affect, the correctness of the computation graph cannot be affected, right. So, I mean in short we can say that let us say we have like 100 filters in one layers. So, we can say that each GPU, if we have let us say 5 GPUs, you can say that each GPU can hold 20 filters, okay. I mean you can assume the filter size is so big, or that there are so many number of channels that each GPU can only hold 20 filters, right. So, that is the tensor parallelism. So, in model parallelism, so let us say we have this is the entire model where these are the layers. So, in model parallelism we are saying that each of the GPU can hold some number of layers, right. In tensor parallelism we are saying that we are further breaking the layers into tensor, and then we are further breaking the layers into like fragments of the layers, or maybe fragments of those tensors, and we are saying that each of the tensors will go to the particular GPU. It can happen like some layers can be very big. So, maybe one GPU cannot hold all the parameters of all the parameters of that particular layer. So, it may go to like different GPUs. So, that is a tensor parallelism. So, we need to split the tensor into n chunks along the specific dimension. Like if we are talking about convolutional neural network where the filters are like 4D tensors, right. So, remember the filters are represented by like age, height and width, and the number of channel, and then number of filters, right. So, you can say that some number of filters can go to different GPUs. So, that is the tensor parallelism. But again, I mean it requires additional communication to make sure the results are correct. So, we can perform the computation of different filters at different GPU, but then to make the final output we have to gather all the computation, right. So, that is the tensor parallelism. Of course, I mean we can divide the model, or you can divide particular layers into tensors, but at the end we need to perform additional communication to make sure the result is correct. So, that is all about this lecture. Thank you very much. See you next time.